Good morning, dear students. Uh, Today we are starting the third module, differential equations and series. And topic of the today lesson is differential equations of the first order. Well, what is the differential equation? It's an equation in which participate derivatives of function, the function and variable on which this function depends, and how to define the order of the differential equation. So actually the highest order of the derivative that contains this equation. And what is the solution of the differential equation? It is a function which, if we substitute it into the equation, we will turn it, so the equation will be true. So if we substitute the function. So let's start with the first task. Here we have a differential equation with the separable variables. And how to solve it? Basically, we separate variables and integrate. Well, it seems that everything is correct here. So we used, nothing missing. So let's start separating variables. So first of all, let's move this part to the right. After that, dividing both parts by this expression, 1 plus e in power of 2x. And after that, divide both parts by y. So we finished separating variables, and now we will integrate. So we will integrate both parts, the left and right. So this expression will be equal logarithm over module y. And this integral will be equal, this is, so e in power of 2x, it is half of the differential of this expression. So the answer will be 1 over 2, a logarithm of 1 plus e in power of 2x. And also we need to use arbitrary constant. Oh, yeah, here I have a mistake, by the way. Let me let me fix it. Okay, so 1 over 2, and here will be the square root. Okay. So plus constant c, but in some cases it is more convenient to write it as a logarithm of c. When we have everywhere logarithms, it is convenient to write a logarithm of module c. So then we will receive logarithm of y equals this expression. And in this case, we can write down y explicitly. So what we will have, y equals c multiplied by this square root. So remember in the properties of logarithms that logarithm of sum of logarithms equals logarithm of product, and coefficient before logarithm can be moved here as the power. So this is the final answer. Any questions about this exercise?
No.
Okay, no questions, so let's move to the next exercise. 1b. So the next equation, again, it is the equation with the separable variables. So let's start separating variables. Let me write down y prime as dy by dx. And now separating x and y. So first of all, let's multiply this part by dx. So both parts will be multiplied by dx. So here I will receive xy dy. And also we will divide both parts by x. So we finished separating variables. So now we will integrate. So this integral will be equal 1 over 2 y square. And what about the second, this integral? So it will be equal 1 over x minus x dx. So it will be equal logarithm of modulo x minus 1 over 2x square plus c. And the solution will be the following. So 1 over 2 y equals logarithm of x minus 1 over 2x squared plus c. Here, well, we can express y explicitly, but we will separate the solution by two branches, so minus square root plus square root. So such form of the answer is acceptable. Any questions about this exercise?
No.
Okay, if no questions, let's move next. So here we will solve the following differential equation with using substitution. So let's first of all write down the equation. So how to solve? Let me make the following substitution. So z equals 4x plus y plus 1. And by the way, z is a function that which depends on x. So how to express y from this formula? Y equals z minus 4x minus 1. Then y prime will be equal z prime minus 4. So we have everything for substitution. So let's rewrite our equation. It will be the following. So z prime equals z prime minus 4 equals z square. We received equation with separable variables. So let's start separating them. So dz by dx minus 4 equals z square. So moving 4 into the right part. So dz by dx equals z square plus 4. Then so dz over z square plus 4 will be equal dx. So that's what we received. So now let's integrate both parts. So we will receive 1 over 2 arctangents over z over 2. And it will be equal x plus c. And then we will substitute y. So actually, yeah, z equals 4x plus y minus 1. So let's substitute this expression instead of z. So what we are receiving, and now we have the chance to receive the solution explicitly. So arctangents of this expression equals 2 x plus c. Then 4x plus y plus 1 will be equal. Okay, let me also multiply by 2, so it will be equal to tangents of 2x plus c. And now we will express y. So y will be equal to tangents minus 4x minus 1. And that's it. And this is the general solution. Any questions about this exercise?
No questions.
Okay, no questions. So we actually, yeah, we do substitutions for such form of differential equations. So it doesn't matter which power do we have. So it's like a polynomial from x and y. And we do such substitution. So substitute this expression with another variable. Okay, if no questions, we are moving to the task number 3. Let me check how many equations. Yeah, so here we have homogeneous equations. So interesting kind of differential equations. So let me first of all write it down, and after that we will start solving. So 3y squared plus 3xy plus x squared dx equals x squared plus 2xy dy. This is a homogeneous equation. How to define it? All variables, so x and y here are so have a power of 2. So this is a power of 2, and xy, actually this is a power of 2 expression. So power of 2, and this is power of 2. So we have the same power for all these variables. Let we divide both parts of equation by x. So by x squared, and what we will receive. So 3 y squared over x squared plus 3 y over x plus 1 dx equals 1 plus 2 y over x dy. And then we will do the following substitution. So we will substitute u, so u equals y over x. And u is a function that depends on x. So then y equals ux, and y prime equals u prime x plus u. So we will substitute everything here. Yeah. Let me rewrite also this equation. Yeah. So I will write down here dy over dx, dy by dx. Okay. So let's rewrite the equation. So what will we have? 3u square plus 3u plus 1 equals 1 plus 2u and multiplied by u prime x plus u. Actually, it will be the equation with the separable variables. So it is the equation of with separable variables, and we will separate. We will start separating them. Du by dx multiplied by x plus u equals 3u squared plus 3u plus 1 over 1 plus 2u. So let's subtract u from both parts. And let we also write down a solution in a more compact way for our convenience. So then what we have here, so du by dx equals multiplied by x equals so this expression minus u and minus 2u square. Then we will simplify it a little bit. U square, so here will be 2. And by the way, we receive here a perfect square. So it will be useful for us when integrating. Then continue separating variables. So what we will have? So dx over x will be equal 1 plus 2u divided by u square plus 2u plus 1 du. So now let's start separating variables. No, we separated variables, so now we're integrating. So this integral will be easy to calculate. So logarithm of module x plus c. I'm not sure if it makes sense to write down constant as a logarithm here. We always can change it. And what about this integral? So what do we have here? So let's so let's remember how to calculate how to integrate rational fractions. So I will add, so it will be 2u plus 2 and minus 1. So what I receive here, so minus 1 here, so actually du. Yeah, du will be moved here. And what, so then what else? So this integral, so what do we have in the numerator? It is actually the differential of the denominator. And what about this integral? So in the denominator, we have the perfect square. So u plus 1 in power of 2, and actually du can be rewritten as du plus 1. So it will be the same. So we have logarithm of module of this expression. And minus, not minus, plus 1 over u plus 1. And now let's write down the solution. So logarithm of x plus c equals this expression. And also don't forget to substitute, so to return to old variables. So here what will be x square over y square. Oh, stop, y square over x square. And 2 y over x. And here as well y over x. So this is the final answer. I don't see any chance to turn it to explicit form, so to express y explicitly. So we leave this answer like this. Any questions about this exercise?
No questions.
Okay, no questions. So actually not for all differential equations we can write down the answer in explicit form. And actually most differential equations have no exact solution. But yeah, maybe we will solve such equations in other courses. Okay, so let's have more practice with homogeneous equations. So we have the following equation. So here we just do the substitution. So u equals y over x. Then y equals ux. And y prime equals u prime x plus u. So substituting everything into our equation. So u prime x plus u equals u plus sine of u. So what can we simplify? So first of all, we will destroy u. So u prime x equals sine of u. And by the way, actually, let's write down our derivative as du by dx. So separating variables. So what do we have? Du over sine over u equals x equals dx over x. Now we will integrate. Okay, I don't really remember logarithm of seconds, but or not seconds, coseconds, but yeah, let me Google a little bit. So this logarithm is logarithm of module x plus logarithm of module c, and so what will be logarithm of coseconds? Let me check. Nice, actually no information here. Okay, let we check in lectures the table of integrals, because I really don't remember logarithm of seconds. So that is not calculated often. So yeah, we'll look at now. I remember that, if I'm not mistaken, logarithm of tangents x over 2, but really not not sure. So it's a good idea to double check. So it seems to be a table of integrals. So yeah, so it was correct. So tangents u. So we will write down the solution. So logarithm of tangents equals the logarithm of module x plus logarithm of c. So then we will express u here, so it can be expressed. So we can write down it explicitly. So tangents of u over 2 equals cx. Then u over 2 equals arctangents over cx. Well, actually, let's write down as so u equals 2 arctangents. Now we'll substitute y over x. And y equals 2x arctangents of cx. So this is the final answer. So here we had such chance to write down explicit solution. Any questions about this exercise?
Could you scroll up a bit?
Yeah, sure.
Yeah, no questions. So,
Anybody else maybe has questions?
No questions.
Okay, no questions. So we are moving to exercise 4. So one more interesting example. So one more kind of so it will be equation that we will reduce to homogeneous. So the equation is the following. So dy over dx, dy by dx equals x minus y plus 1 over x plus y minus 3. So first of all, we need to check if actually this equation can be reduced to homogeneous. How to check it? We need to calculate the following determinant. So with the coefficients for x and y. So the first row 1 and -1, and the second row 1, 1. So so the first row for numerator, the second for denominator. And actually we can see here that this determinant equals 2, and it is not equal to 0, so the equation can be reduced to homogeneous. And how to do it? We will do the following substitution. So x equals x1 plus h, and y will be equal y 1 plus k. X and k are numbers, so they are real numbers. And now let's rewrite our equation. So what we will receive? So dy 1 over dx1, it will be equal x1 plus h minus y1 minus k, and here x1 plus h, and plus y1 plus k minus 3. Then we will solve the next system of equations. So equations with respect to x and k. Yeah, and by the way, let's rewrite the order of variables or coefficients that we have here just for our convenience. So we have to solve the following equation. So a system of linear algebraic equation with respect to h and k. So we so these parts must be equal 0. These parts. So h plus k minus 3 equals 0. And now let's start solving. So first of all, of course, moving coefficient. So 3 members to the right. So what do we have here actually? So if we add both one equation to each other, so we will receive 2h equals 2. So h equals 1. Then k equals 2. So, and if we substitute them, yeah, so it will be true. So now what do we have here? So now let's do the substitution. So plus 1 minus 2 plus 1 plus 2, and actually constants will be destroyed. So they will be eliminated. So what I will receive here, so the following expression. Why they are not erasing? So erased. And now let's divide both parts. Let's divide both the numerator and denominator of the right part by x1. So what I have here, so 1 minus x minus y1 over x1, and over 1 plus y1 over x1. And now let's do the substitution that we do for homogeneous equations. So dy by dx, dy1 by dx1 equals u, du by dx multiplied by x plus u. So writing down the equation with the substitution. So what do we have here? 1 minus u over 1 plus u. And now separating variables. So 1 minus u plus u square. Oh, stop. Minus u and minus u square. Sorry. And then now, so continue separating variables. So dx by x equals 1 plus u over 1 minus 2u minus u square. So having the following integral. Okay, yeah, let's write down as integrals, and here du, by the way. So this expression will be equal logarithm over module x plus logarithm over module c. And then let's calculate this integral. So let's rewrite the denominator a little bit. So we will extract the perfect square in the denominator. So what do we have? 2 minus 1 minus 2u minus u square. So 2 minus 1 plus u in power of 2. And what do we see here? Actually, so in the numerator, there is something similar to the differential of the denominator. So if we differentiate the denominator, we will receive a minus 2, 1 plus u du. So we have minus 1 over 2 and differential over the denominator. So it will be minus 1 over 2 logarithm over module 2 minus 1 plus u square. So let's write down the answer. So it is the following. And now we will start moving to old variables. Yeah, by the way, I forgot that here we have everywhere x1. So we'll replace everywhere x with x1.
So x1 also should be the dy1 over dx1.
Yeah, actually, dy1 by dx1 equals dy by dx because there are constants. Yeah, but it's a good idea to not to break indices anywhere.
Uh, I'm asked if x should be with 1,
So,
where du over dx, a bit lower.
yeah, sure. Nice
Uh,
catch, thanks.
yes, thank you.
So now so now we will return to old variables. So a logarithm f module f plus logarithm of c. And by the way, we can even remove a logarithm out from here. So first of all, let's do this. So cx1 will be equal 1 over this square root. And then we will move to old variables. Okay. Let me write down in a more accurate format. So y 1 by x over x1, and after that we will return to x and y. So c x plus 1, and here y plus 2, and x plus 1. Now we actually can even write in the explicit form. Oh no, it is hard to it will be hard to write down in explicit form because we have square here. So let we leave it like this. Any questions about this exercise?
No.
Okay, if no questions, let's have a break for 5 minutes, and then we will continue solving different other kinds of differential equations. Okay, let's continue. Let me share my screen. So now we will solve linear equations. So what actually does mean a linear equation? So it is an equation for which derivative and the function, y prime and y have the power of 1. And how to solve linear equations? So there are two methods. First of them, it is a method of variation of arbitrary constant. The second method is the method of the Bernoulli's method. Let's solve this equation with the method of variation of arbitrary constant. Yeah, actually there are two linear equations can be homogeneous and no homogeneous. So linear equations are homogeneous if there are no free members, but here we have a free member x cube, so it is non-homogeneous. How to solve with using method of arbitrary constant variation? So we need to solve the correspondent homogeneous equation. Actually, the homogeneous linear homogeneous equation, it is also the equation with the separable variables. So let's separate variables and integrate. So what do we have? Dy by y equals minus 2 dx by x. Then, yeah, of course, we will integrate them. So dy by y equals logarithm of y, of module y. And this expression equals, so this integral will be equal minus 2 logarithm module x plus logarithm of c. So now let's writing down the solution, and now we will express y explicitly. So y will be equal c over x square. Then we will assign c as a function that depends on x. And after that, we will have to substitute this. So we will substitute this expression into the initial equation. So what do we actually have? So for for the left part, so y prime will be equal. So moving so x4 in the denominator. So what do we have? C prime x square minus 2 cx plus 2 plus 2 c over x cube. So y over x, so c over x cube, and equals x cube. So we will find c from x from this equation. Now expanding this fraction, so what we will receive? So cx over 2 minus 2cx over x cube. over x in power of 4. So it's actually 2cx over 2c over x cube. So then what we can see that c is eliminated in this equation, and always when we use when you use method of variation over arbitrary constant, if c is not eliminated after the substitution, it means that you made a mistake somewhere. And here c is eliminated, so it means that there is no mistake. So c prime equals x in power of 5. Then c equals 1 over x, 1 over 6x in power of 6 plus c. Let we add a wave here just to mark this as so this is arbitrary constant, not not a function. And now we will substitute c into this expression. So y equals 1 over 6x plus c with a wave divided by x in power of 4. So let's simplify it a little bit. So y equals 1 over 6x square plus plus c with a wave over x in power of 4. So this is the answer. Any questions about this exercise?
No.
No questions. Okay, so moving to the next exercise. Yeah, so as I told you before, there is one more method of solving differential equation. So linear equation is Bernoulli method, and here we have the example. So the solved example Bernoulli method, but we will use such method for another kind of equation. So for Bernoulli equation. So what is Bernoulli equation? It is quite similar to linear equation, but remember also contains y. So it is similar to linear equation. So we have y prime in power of 1, y in power of 1, and one more component where y can have any power. So how to use Bernoulli's method? Bernoulli method. So we write down y as a variable, as a product of functions u and v. U and v are functions that depend on x. So u prime equals or y prime equals u prime v plus u v prime. So now let's write down the equation with this substitution. So u prime v plus uv prime plus 2x uv equals to x cube u cube and v cube. Now let's so in the left part let we move u out of brackets. So we will factorize this part. We will move u out of brackets. So if I move u out of brackets, what I receive? So v prime plus 2xv. Functions u and v will be found from the following system. So actually how Bernoulli method works. So we assign this expression in brackets as to 0. If this expression is equal to 0, it means that u prime v equals 2x cube u cube v cube. So let's solve. Let's first of all find v. So dv by dx equals minus 2xv. Then let's separate the variables. Dv over dv by v equals minus 2x dx. Then we will integrate both parts. So a logarithm of module v equals minus x square plus c. Okay, plus logarithm of c. So then we have that, so having receiving the next expression for v, so v equals e in power of minus 2x square. E in power of x minus x square. Yeah. So done with this. And then we found v and now finding u. So we will substitute everything instead of v into this expression. So we will substitute this exponent instead of v. But first of all, let's also write down, so du over dx, and here exponent, so e in power minus x square, and here e in power minus 3x square. So now we are finding u. So du by dx, yeah, multiplying by e in power of x square. So we're receiving here e in power of minus 2x square. So du over, okay, du by u square equals this expression by dx. And now we will integrate both parts. Okay, so this integral will be equal minus 1 over 2 1 over 2 u square. And what about this integral? So it will be the following. Okay, so it will be quite complicated, but we will be able to calculate it. So let's write it like this. So 2x by x square. And what we actually have here, so 2x is, so 2x dx is a differential of x square. So and now let's make a substitution just for easier calculation. So t will be equal x square, and you will see that this integral will look simpler. So integration by parts that you already know. Okay, write like this: u1 equals t, and du1 equals dt. Then dv1 equals e in power of minus 2t dt. Then v1 equals minus 1 over 2 e in power of minus 2t. So we have the following expression. So yeah, and this multiplied by t, and plus 1 over 2 integral over e in power minus 2t dt. So now receiving the following. So minus 1 over 4 e in power of minus 2t plus c. Yeah, let me check if we use c or now here. Yeah, okay, we'll use c here. So let we move also also minus 1 over 4 in power over minus 2t out of brackets. So I will receive 1 plus 2t plus c, and with returning to old variables. So what I have, e in power, so here will be e in power of 2x square, and here 2x square. Yeah, so correct. And now we will express u. So this expression equals this expression. So we will express u. So okay, let's erase minuses here. Oh yeah, we'll divide by minus 1. And then also we multiplying by 2 both parts. And after that, so what I have, u equals plus minus and square root of so 1 over this expression. So it will be equal so 1 over this. And y, so returning to y. So y equals uv. So it will be equal plus minus this expression multiplied by e in power of x, if e in power of minus x squared. So this is the general solution. Any questions about this exercise?
No.
Okay. So moving to the next equation, to the next exercise. Actually, yeah, this Bernoulli equation. So B will be your home task. So you will solve in your own, and now we will solve equations in total differentials. So 7a. So now remembering some stuff from the previous lessons. Restoring function by its total differential. So we'll write. So first of all, I'm writing down equation, and after that I will explain. So x minus y square plus 3 dy equals 0. So let's check if this equation is equation is a total differential equation. So we need to check if this expression is a total differential of some function. So reminding you how to do it. So P equals this expression and q equals this expression. So we need to check if dp by dy equals dq by dx. So dp by dy equals 1. Then dq by dx equals 1 as well. So dp by dy equals dq by dx. So it means that we have a total differential of the function. So now we will restore the function by its total differential, reminding you the formula. So u from xy equals so the following integral: x from x0 with index 0 to x, p from x and y0 integrated by dx, and plus so integral from y0 to y, and q is integrated by xy. So q is integrated by dy, and y is without 0, so just a variable, not a number. And how to choose x0, y0? Actually, we can see that 0 is included into the domain, and it's always convenient to choose 0. So we will integrate. So this part will be so from 0 to x, and the expression x plus 1. So x plus 1 integrated by x. And what about q? So from 0 to y, and we integrate this expression, x minus y squared plus 3. So we have 1 over 2x squared plus x plus xy minus 1 over 3y cube plus 3y. So actually we have received the restored the function by its total differential. So if I substitute x here, so we have such expression. If I substitute 0, I receive 0, and analogically to this integral, if I substitute 0, I receive 0. And the final answer will be the following. So this expression equal to c. And so this is the general solution, and we cannot express y explicitly in this case. But yeah, so we can see that solving equations in total differentials is really fast and easy. Any questions about this exercise?
No.
Okay, no questions. And for now, let we just have a look at 7b. So we have the following differential equation. So so we have the following equation: x square y square minus 1 dx plus 2x cubed y dy equals 0. So first of all, so differentiating this expression by y, so we will receive 2x square y, and if we differentiate this expression by x, we will receive 6x square y. So such expressions, but dp by dy, so doesn't equal dq by dx. So this is not a total differential equation. However, we can see that they are quite similar. So but different coefficients before them. So, what to do in this situation? We actually can find an integration. Integrating factor. Integrating factor is a function that transforms the initial equation into total differential equation. So how to find it? So we need first of all to calculate such expression. So we need to subtract dp from dp by dy from dq by dx and divided by q. So we received such expression. And after that, mu from x, so integrating factor will be found from this expression, from this differential equation. So d logarithm of mu by dx equals, so in our case, minus 2 over x. So we found mu, it equals c over x square, and we actually can assign any value. So let's assign 1 in our case as integrating factor. So we have integrating factor 1 over x squared. If we multiply by the initial equation by mu, so we will receive the total differential. So if we differentiate by this part by y, we receive 2y, and if we differentiate this part by x, we receive 2y. So we received total differential equation, and now we can restore the function given by total differential. However, pay attention to this expression. So we cannot choose the point 0, 0 as point x 0, y 0. So 0 is not included to the domain. So we can use 1 for x. So x0 will be equal 1. So we integrate this expression so from 1 to x. Yeah, and actually for y 0 we can use 0. So here we have only minus 1 over x, and here we integrate from 0 to 2, from 0 to y to xy. And what we actually received finally, so the final solution will be the following: 1 over x plus xy squared equals x. Yeah, we actually can, so we can eliminate 1, so it will be part of arbitrary constant. Any questions about this exercise?
No questions.
Okay, no questions. And now we have to solve the Cauchy problem, so or initial problem. So let me write down the equation, and I will explain what do we have to do here. So 1 plus y square over 1 plus x square, and y from 0 equals 1. So it is a Cauchy problem. So this condition is called initial condition or Cauchy condition, and the equation with initial condition is so together. It is called as a Cauchy problem. So so how to solve a Cauchy problem? Actually, we have to find first of all general equation, general solution of the equation, and after that we will look. So we will have to find arbitrary constant c. So first of all, let's start So let's do what we did before. So as we can see, this is an equation with separable variables. So 1 plus y square over 1 plus x square. So dy by 1 plus dy over 1 plus y square and dx over 1 plus x square. By the way, let we solve in one, start solving in one row. So what do we have here? So arctangents over y equals arctangents of x plus c. So then y equals tangents over arctangents x plus c. So we found the general solution, and now we have to find the partial solution. So now I substitute 1 instead of y and 0 instead of x. And what I receive? 1 equals tangents of 0 plus c. And actually, so we can see that tangent c equals 1. So it means that c equals p over 4, because tangents of p over 4 equals 1. And now writing down their partial solution. So y equals arctangents of x plus so y equals tangents of arctangents x plus p over 4. And this is the partial solution. Any questions about this exercise? So actually, nothing frightening with just with finding general solutions. Just you have to solve this equation with respect to c. Yes, Stanislav, a question?
Shouldn't x plus p divided by 4 be in brackets?
Why? I don't
Like,
understand. Yeah, so
in the end here is
well, we have arctangents of x, but no. P is not p over. So do you mean the argument of arctangents?
yes.
No, because so what do we see here? Arctangents of y equals arctangents of this arctangents of x plus c. And how to find y? We take tangents of the whole this expression. So actually, arctangents of x lives its own life here, and p plus 4 is and so so is leaves so it is just added to arctangents of x. So it is not the argument of arctangents, not a part of it. So have I answered your question?
Yes, thanks.
Yeah, of course we can so we can transform somehow this expression with using different trigonometric formulas, but really we don't need to do it. Well, let's solve one more equation and then we will finish. By the way, maybe more questions or no questions about this exercise? Okay, if no questions, let's solve one more exercise. So 8b. So we have the following equation. So x squared plus y squared dx minus x dy. Well, it is the homogeneous equation. As we can see here, actually, this expression has power of 1 because of square root. So we will use the following substitution. Yeah, it equals 0. So y, yeah, first of all, yeah, dividing the equation over x. Yeah, and by the way, writing down the initial condition. So y from 1 equals 0. So dividing by x. And here will be just dy. So what I actually will receive here, so dy by dx equals such expression. So y over x equals u, then y equals ux, y prime equals u prime x plus u. So we will do the substitution. So u, okay, let's write down as du by dx. And we will have u plus 1 plus u square. So it will be simplified. So x du by dx equals this expression. So then du by this square root equals dx over x. So we have long logarithm of u plus this square root and equal, yeah, by the way, let me write down, let me put integrals here. So it equals logarithm of x plus logarithm of c. So yeah, don't lose modules. And now we will write down that so such expression equals cx. Cx. So let we substitute. So let's return to old variables. So y over x, and here y square over x square. And now let's find the constant. So what will be substituted? So y from 1 equals 0. So here 0, 0, and here will be 1. So actually c equals 1. So the partial solution will be the following. So this expression. I'm not sure if we can write down it in explicit form, so we will so it will be remain like this. Any questions about this exercise? Maybe about the whole lesson, about previous lessons?
No questions.
Okay, if no questions, we will finish. Have a nice day. Stay safe. And thank you for your attention. Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Thanks for the